Let's try a hypothesis test for a difference in means. So I'm going to start with some data in StatKey, randomization hypothesis test, test for difference in means, and we'll do a randomization test and then apply the central limit theorem for comparison. Data I want to look at here is from the Mindset Matters study, which hopefully you've read about several times in the book now, but we should get a reminder about what the variables and what the study are. So let's open up a new tab for StatKey and go over to the book website part of it. And then we want data sets for our third edition. And down at the bottom here is the data set description. And let's go search for mindset. All right, and let's blow this up a touch. Okay, so we have a study of perceived exercise with maids, 75 observations, 14 variables. And the variables we're concerned about are the treatment condition, 0, they were uninformed, 1, they were informed. And then back here, they have a variable called weight change. And notice there isn't a weight change variable here, so they must mean the difference in the weights from the beginning and then 4 weeks later, weight 2. And again, a reminder about the details. 2007, Harvard psychologist recruited 75 female maids working in different hotels to participate in a study. She informed 14 maids, randomly chosen, that the work they do satisfies the Surgeon General's recommendation for an active lifestyle, which is true, giving them examples for how and why their work is good exercise. The other 34 maids were told nothing, uninformed. Okay, then we have characteristics were recorded in the initial phase and then 4 weeks later after some were informed. Again, if they were missing a weight, then they've been removed. There are other places where data was missing, so there'll be blanks in there. So I just want to double check about the data we have. So StatKey claims that the uninformed group had a mean weight change of negative 0.2, and the informed group that believed there was told their work was healthy and active had a weight change of 1.785. And then the difference in the two of them, group 1 minus group 2, so the average average weight change of the uninformed minus the average weight change of the informed was 1.59. So if I'm interpreting this right, if we take the second weight minus the first weight and it's negative, they lost weight over those 4 weeks. If we take the second weight minus the first weight and it's positive, they gained weight over the 4 weeks. So I'm just going to double check that I'm interpreting this data right. Again, this example is in the book also. So I'm going to go to my copy of it. So here's the original data set. And let's blow this up a little bit. One more time. All right, so conditions: 0 uninformed, 1 informed. Right? Again, we got to know what our variables mean. And then we have weight, and those must be weight in pounds for an adult woman. And then I believe the weight change variable would be weight 2 minus weight 1. So I copied those into another tab, and I kept track of, for each person, the condition, informed or not. So this person was uninformed. Their initial weight was 137. Their weight 4 weeks later was 137.4, which means they gained 4.4 pounds. Another person, uninformed, started at 150. 4 weeks later was 147, so they lost 3 pounds. Scroll down. This person was informed, weight was 170, then 172.6, so they gained 2.6 pounds, and so on. So this is the variable we're analyzing here. And the mean of group 1, which is the average weight change of the uninformed group, was negative 0.2 pounds, which means on average, the uninformed group lost 0.2 pounds over 4 weeks on average. And then the informed group, which should be all these weights down here associated with the 1 that they were informed, they on average lost negative 1.785 pounds. And the difference, negative 0.2 minus negative 1.78, is about negative 1.59-ish. And that matches what StatKey has here. So I'm just double checking that I have the right data and I know what the data means. If you don't have that, you can't do a hypothesis test. No point in running it if you don't know what you're talking about. All right, so then in StatKey, for a difference in means, we assume there's no difference. Why should there be a difference? Alternatively, somebody might claim, well, if you believe your work is active, then that positive thought might help you be healthier somehow. Maybe you'll eat better. Maybe you'll pay more attention to the way you move yourself while you're doing your work. Who knows? So alternatively, I might say, no, the informed group lost more weight. So that means I should see a significant positive difference in the averages of weight change. So I'm going to write that down. It's a lot. Okay, so again, this is a kind of complicated situation. We get a whole bunch of variables. So we have mu, and our mu here is the average weight change of, I'm going to say adult women over 4 weeks. All right, so that's my population parameter in general. Now I have two different groups. I have to break them into their groups. So then I'm going to have a mu1, which is the average weight change of the of women who haven't been informed that their work is an active lifestyle. So average weight change of an adult woman who has not been informed. That their work represents is active exercise. Just trying to put that in my words to the best of my ability. And then group 2, that's my best mu today. Similar average weight change of an adult woman who was informed. All right, so number one, we got to know what the population parameters are. Then we'll get to our sample in just a little bit. Next thing, I need to go to the hypotheses. So my hypothesis, initially, whenever we're looking at two groups, is there's no difference. So they're the same. So mu1 equals mu2. That's the standard for when we're comparing two groups. If you consider that we could rewrite that by subtracting mu2 to the other side, we could say meter mu1 minus mu2 is 0. So the difference in means is 0. That would be an alternate, a null hypothesis, sorry, because it's got an equals in it. And then someone might say, no, 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 I think there is going to be a difference, right? That'd be the conservative thing to do, a not equal. But you might say, well, knowledge is power. Maybe knowing that will help them be healthier. So I'm going to go with that biased, slightly biased idea. Maybe it's not biased. Maybe I have some good reason to think that besides this study. So I'm going to say mu1 is going to be, let's see, a less negative. Let's see, I got to look at that in a number line for a minute, make sure I get that right. Let's see, X bar 2 was negative 1.78 something, 5. And X bar 1, the uninformed group, was negative 0.2. That's over there. And so I think that one's going to be bigger, right? Because it's to the right on a number line. All right, so I'm going to go with this direction. Oh, no, I put it the wrong way. The greater than part needs to go to X1. All right, try again, Gare. This is a tough one to think about. There's a bunch of things going on there. That looks better. Yeah. The uninformed group will have a greater difference. And again, that difference was weight 2 minus weight 1. And so if that is positive, that would be a weight gain. And again, sometimes I have to write this stuff out to make sure I understand what I'm talking about. And if weight 2 minus weight 1 was negative, well, that means they lost weight. So that would be a weight loss. Okay, I think I'm on the right track here. We could rewrite that by subtracting mu2 to the left. So then we'd have mu1 minus mu2 would be greater than 0, which is what our sample data suggests. So I'm going by this, what my sample data suggests. Remember, every sample is different. Another sample of Maid's, they might be switched. We don't know. We'd have to get that sample and see. All right, so interpretations of these, again, H0 means no difference in weight change. And then my alternative hypothesis means the informed group lost more weight. And this one, again, is one of the harder interpretations of anything we've done yet. All right, I think I'm on the right track. Significance level, I'm just going to do the standard. Alpha is 0.05, right? 5% significance level. Okay, so again, before you can run your hypothesis test, you've got to state your population parameters, understand clearly what they mean. Then you have to be able to state your hypotheses. And then you really need to be able to explain your hypotheses to anyone, state them in plain language like that your mom would understand. All right, well, once you get that down, then you take a look at the sample. So let's see, new page. Let's look at sample data. All right, so for the sample data, we have X bar 1 was about negative 0.2, and X bar 2 was about negative 1.785. I better double check that. Negative 1.75 over here and negative 0.2. Yep. And the difference is about negative 1.59. Okay. Or positive 1.59. Sorry. And then we've got the difference in means, which so this would be our sample statistic or test statistic. Sample statistic, aka test statistic, not to be confused with a standardized test statistic. Oops, statistic is the x1, the mean 1 minus mean 2, right, which is uninformed minus informed. So uninformed mean weight change, and I'm just re-summarizing what's over here. So whatever the description of the population parameters are, you should have a similar description for the sample statistics or statistic, and this would be the informed. mean weight change. All right, and so we have that is about positive 1.59. And what we need to know is how far apart is no difference, right? A difference of 0. How far is 0 from 1.59? Sometimes they're close together on the number line. Depends on whether you're how zoomed in you are on the number line. Sometimes they're far apart. Like if we're really zoomed in, they're far apart. If we're zoomed out, they're close together. Hypothesis tells us figure out whether 0 and 1.59 are close or far. All right, so now I need to figure that out. So we're going to first do this with stat key, and then we'll try a spreadsheet using the central limit theorem. So I have my null hypothesis, I have my data. Once you have the two of those, next step is generate at least 6,000. Okay. Once we have that, we decide what tail test it is. Well, that's the alternative hypothesis tells us that. Alternative says we are doing a right tail test, which makes sense because the difference in means is positive, and positive is to the right of the null hypothesis value of 0. All right, so then I choose right tail. There we go. And then I plug in this number right there from the sample, the 1.59. 1.59. Looks good. Okay. And so there's my 1.59 on the bottom. So again, to do a hypothesis test, you have to have a sampling distribution, and you can get that from either a randomization like this, or you can get that from the central limit theorem. You have to know where the null hypothesis value is. That's always going to be in the center of the distribution. Notice the axis down here. What is this axis down here? This axis down here is weight change. So here's a weight change of 0, sorry, difference in average weight change, a little more complicated. Difference in average weight change of 0, difference in average weight change of 1.59. Up here is my p-value. Let's sketch it. All right, so a sketch based on the hypotheses and the randomization and the sample statistics looks like this. Where'd my magic pen go? There it is. All right, so we're going to draw that horizontal axis. And in this case, that would represent mean weight change. Mean weight change. And in the middle, let's draw my normal distribution, looks something like this. And in the middle here is a mean weight change of 0. That's assuming that on average for the population, the average weight of the uninformed group minus the average weight of the informed group, there's no difference. They're about 0. Well, we found that our sample data has a change out here. So my average from my first group minus the average from the second group is about 1.59, and that's right here. So on the axis goes whatever the parameter value is from the null hypothesis, whatever the sample statistic value is gets marked. And again, it could be on the right, could be on the left, depends on the situation. This one happens to be on the right. And then out here are other possible samples. And the other possible samples out in that tail, that represents our p-value. And the p-value is the proportion of other possible samples that had a greater difference. And StatKey says the probability of that happening is 0.0043. Oops, 3. Double check I got that right. Yeah, 0.0043. So again, null hypothesis value, sample statistic or test statistic goes down there, and then up above, StatKey calculates the proportion of other possible samples that had a greater difference when we were expecting no difference. That's an interpretation of the p-value. The probability of finding another similar sample of 75 hotel maids where the average weight change difference between the two groups is bigger than the difference we found of 1.59. Probability of that happening is 0.0043. That's a pretty small probability, assuming there should have been no difference. So either I have a weird sample that's just naturally unusual, or there was something wrong with my assumption that there should be no difference. And so we're going to say, well, I'm pretty sure we have a good sample here. So the problem isn't my sample. The problem was the assumption that there should have been no difference. That's incorrect. So when we have a small p-value, we reject the null hypothesis. So my decision here, decision's always about the null hypothesis. Reject the null. Conclusion, that's the harder part. The conclusion is always about the alternative. Oops, if I could spell today. Conclusion. So if you reject the null, that means your data supports the alternative. So I would start off with something like, we have sufficient evidence that, what comes next? Whatever the alternative hypothesis comes next. So go back. What was your alternative hypothesis? Hopefully you wrote that out in words. If you didn't, you better figure it out. So my alternative hypothesis, get my highlighter out to emphasize, is this here. So that means the mean, the difference in the means of the weight changes of the two groups is going to be greater than 0. A more casual way to say that is the informed group lost more weight, was what I eventually whittled that down to. So it usually takes me a few tries to get something understandable, especially if it's complicated like this, because there's a whole bunch of things that went into this particular variable. All right. So again, important things. You can't do a hypothesis test unless you know what the parameters for the population are. Once you know that, you need to then be able to state in words and symbols what the null and the alternative hypothesis are, so that when you do the hypothesis test, that is, compare the sample data with what was expected, you can then decide whether you reject or fail to reject the null. So in this case, we're rejecting the null. Our data supports the alternative. And then the next thing we would do is say we have sufficient evidence that, and then state the alternative hypothesis. So I'm going to skip that for a moment because I want to check out what the central limit theorem says about this. So for the central limit theorem formulas that we looked at in chapter 6, you have to have a reasonably large sample size. And usually we say we want the sample size to be bigger than 20. Sometimes some people say bigger than 30 for a mean. And both sample sizes in both groups were bigger than 30. So I can use those formulas. So I'm going to use the spreadsheet that I shared with you a few weeks ago. Got a copy of it here somewhere. And I need to copy my data into that here. So I just need to find the right tab. So I want something about a hypothesis test for two means, two proportion, two means confidence interval. Let's keep going. Two mean hypothesis test. So this is one right here. And this is, what was this one right here? Oh, I was playing around with a similar one before. These are the BMIs of each group. I was trying to see if there was a difference in the BMI 4 weeks later. Let's see, what do we have here? We have the informed group, the uninformed group. So I have them in a different order. Then there were only 40 and 33 because some numbers were missing. So let's see, we have informed minus not informed mean BMIs was negative. So that means, again, this was my informed group. Okay, we don't need to go on this tangent right now. Not informed. Should get back to the regularly scheduled program. The not informed average BMI was higher 4 weeks later than the informed group. So the difference is negative. And then I decided to use a two-tail test to be conservative, that I wasn't sure what was going to happen with the BMI. So with a two-tail test here, I have a p-value of 26%, which is a big p-value, which means I fail to reject the null hypothesis, and I can't support the alternative that there is a difference. The data supports that there is no difference in the average BMI. Okay. All right. So way to use the spreadsheet is delete whatever was data that was there by deleting everything in those columns, and then go grab your data. All right, so I got to be careful about this. I want the uninformed group first. So those are the ones related to the zeros. So I want to grab from, excuse me, allergies are getting to me, this number up. All right, and then in here, call this uninformed, and it's weight change. I'll write that somewhere else and then paste the data in. Oops, since I'm pasting a formula, you have to do a Control-Shift-V, paste special. There's the numbers, make sure I didn't get anything else in there. So negative 1.4 at the bottom, 0.4 at the top, 0.4 at the top, negative 1.4 on the bottom. Okay, I got it that time. And again, because this came from a formula here, I have to paste special, otherwise it tries to paste the formula, not the answer to the formula. Okay, there we go. Copy that in. And similarly, we would, if we were Stacky didn't have the data, we might have to copy it in there. So always be careful. This is the informed group. Informed. We'll shift V to paste special. So again, what I'm doing is edit, paste special, values only. All right, data's in there. What do we have? Double check. Informed, 34 individuals, mean weight change of negative 0.2. That matches what Statkey thought over here. And then mean weight change of the folk. And I got to switch the titles. I did it different than a previous example. Uninformed was first, informed was second. Again, you got to make sure you pay attention to those details. All right, and then the difference is 1.59-ish. That looks good. I'm going to use the simple degrees of freedom, which is remember, degrees of freedom is always one less than the sample size for a t-test, which is what we're doing here. T-test applies to means. So we take the one less than the smaller of the two sample sizes. So 34 minus 1 is 33. Standard error, 0.6-ish. Statkey says the standard error was 0.6-ish, similar. Randomization is going to be a little bit different than what the central limit theorem says, but similar. T value, so this right here is what we call a standardized test statistic. I'll get to that in a sec. Standardized test statistic. All right. And then I decided for mine, I was not doing a two-tailed test. I decided to do a right-tailed test that the difference is greater than 0. So I'm going to make this match my hypotheses. Positive difference in means. It's my interpretation of that. All right, and then so for the right tail test, I get a p-value of 0.0063. The randomization test was 0.0043. Oh, they're in the ballpark of each other. They're both pretty damn small, smaller than 5%. All right, that's 0.4% or 0.6% for this one right here. If you're not sure about that, then put it in percent form to see. All right, 0.6%-ish. Change that back. Try the decimal form. All right, so this is confirming what we found in the randomization. So let's summarize. What do I want to know? 0.6, 2.6-ish. And hopefully you get used to these in the homework. So applying the central limit theorem. So according to central limit theorem formulas, again, hopefully you found the cheat sheet I left for you for this. The standard error is calculated by taking the standard deviation of group 1, squaring it, divided by the sample size of group 1, adding that to the similar fraction standard deviation of group 2 squared, divided by the sample size of group 2, and then you take the square root of that sum, and the spreadsheet is set to do that automatically. You could also do that on a scientific calculator if you really wanted to, but why bother since you needed the spreadsheet to get the standard deviation in the first place? Use the spreadsheet. And our standard deviation was about 0.6, what? 0.60085 if we wanted that many decimal places. So I'm looking right here. Then we have to get the standardized test statistic. In general, a standardized test statistic is a fraction, and it is whatever the null hypothesis says minus whatever the sample statistic says divided by the standard error. So in this case, I have a difference in mean, so that would be x bar 1 minus x bar, got that order wrong. Back up, reverse. It should be sample minus null, because this is like a z-score. Should be the sample value minus whatever the null says, divided by the standard error. There we go. So the sample, that would be x bar 1 minus x bar 2. The null says it should be 0. And then the standard error is that crazy square root there. Sample standard deviation 1 squared over sample size 1 plus sample standard deviation 2 squared over sample size 2, square root of that whole sucker. And that's already built into the spreadsheet. And according to my spreadsheet, I'm getting about 2.6-ish. 2.63855. And then to see what the p-value associated with that is, this is now called a t-score. Why a t-score? Well, because we are doing a mean, and means use t-distribution, not the normal distribution. So to get the p-value, you need a normal t-distribution calculator. And this is all in the book and the previous videos. So the spreadsheet has one built in. So if we look back at the spreadsheet, zoom in on this a little bit more. I'm doing the right tail one. You can see that I'm using the t-dist right tail formula for that. And it's giving me the 0.00630 to 5 decimal places. And it's based on two things, that particular t-score, and we're using degrees of freedom, which is 1 less than the smaller sample size. The spreadsheet, again, does that automatically for you. And again, 0.00630. We could check at stat key too. Stat key is nice because it draws a picture of the t-dist. And what that picture should do is pretty much match what this would look like if you draw a smooth curve through it. So let's go open up a new stat key tab and go to the theoretical t-distribution. It says, hey, what's your degrees of freedom? 33. And then it wants to know which tail do you want, left, right, or 2. I'm going to go right. And my t-score was 2.600 something. Let's see. 2.63855. It's over here. 63855. So enter your t-score. And according to the theoretical, it's about 0.0063. And that's the sketch of it. And again, that pretty closely matches the smoothed out version I drew of this earlier in my notes when I was sketching that randomization. Right there. So that was my best interpretation sketch of this or that. Either way, what's going on here? Well, I have a similarly small p-value. Small p-value means reject the null hypothesis and support the alternative. So this here implies your decision is to reject the null. And your conclusion is to write a sentence that says you have sufficient evidence to support whatever the alternative is, and you're going to state, oops, wrong button, the alternative in a way that me and your mom would understand. In order to do that, you have to have sufficiently defined your parameters and your hypotheses in words. That's the hard part. All right, so this is like the culmination of our work all quarter. We've been working toward this all quarter. This probably is one of the hardest ones yet because we had to play with the data a little bit and then look at a difference in means, which requires a significant amount of brain power. And I can't think through this without writing down a significant amount of stuff to think it out, right? So all these side notes I was writing over here were me trying to puzzle through what does this all mean? All right, keep up the good work and get in touch with me if you have any questions. Have a great day. I'll see you in the near future.